In mathematics, in the study of dynamical systems, an orbit is a collection of points related by the evolution function of the dynamical system. The orbit is a subset of the phase space, and the set of all orbits is a partition of the phase space. That is, different orbits do not intersect in the phase space. Understanding the properties of orbits by using topological methods is one of the objectives of the modern theory of dynamical systems. For discrete-time dynamical systems, the orbits are sequences. For real dynamical systems, the orbits are curves, and for holomorphic dynamical systems, the orbits are Riemann surfaces. Definition: given a dynamical system with T, a group, M a set, and phi the evolution function where we define, then the set is called orbit through X. An orbit which consists of a single point is called constant orbit. A non-constant orbit is called closed or periodic if there exists a T and T, so that for every point X on the orbit, real dynamical system. Given a real dynamical system, I is an open interval in the real numbers. That is, for any X in M is called positive semi-orbit through X and is called negative semi-orbit through X. Discrete-time dynamical system. For discrete-time dynamical system, forward orbit of X is a set, backward orbit of X is a set, and orbit of X is a set. Where is an evolution function, which is here an iterated function. Set is dynamical space, is number of iteration, which is natural number, and is initial state of system in. Usually different notation is used, is written as, whereas in the above notation. General dynamical system. For general dynamical system, especially in homogeneous dynamics, when one have a nice group acting on a probability space in a measure-preserving way, an orbit will be called periodic if the stabilizer is a lattice inside. In addition, a related term is bounded orbit, when the set is pre-compact inside. The classification of orbits can lead to interesting questions with relations to other mathematical areas. For example, the Oppenheim conjecture and the Littlewood conjecture are dealing with the question whether every bounded orbit of some natural action on the homogeneous space is indeed periodic one. This observation is due to Raghunathan, and in different language due to Cassels and Swinnett and Dyer. Such questions are intimately related to deep measure classification theorems. Note: it is often the case that the evolution function can be understood to compose the elements of a group, in which case the group theoretic orbits of the group action are the same thing as the dynamical orbits. Examples: the orbit of an equilibrium point is a constant orbit. Stability of orbits. A basic classification of orbits is constant orbits or fixed points. Periodic orbits. Non-constant and non-periodic orbits. An orbit can fail to be closed in two ways. It could be an asymptotically periodic orbit if it converges to a periodic orbit. Such orbits are not closed because they never truly repeat, but they become arbitrarily close to a repeating orbit. An orbit can also be chaotic. These orbits come arbitrarily close to the initial point, but fail to ever converge to a periodic orbit. They exhibit sensitive dependence on initial conditions, meaning that small differences in the initial value will cause large differences in future points of the orbit. There are other properties of orbits that allow for different classifications. An orbit can be hyperbolic if nearby points approach or diverge from the orbit exponentially fast.